isn't it?
That's true. That's true.
They go by that. They go by, they observe nature and then they follow accordingly. They move on. That's what is seen. So how big is the
I think
location?
it is teaching us how to be more nature lover and not destroy nature like we do most of the time.
Yes, yes, yes. It seems we had taken life very much guaranteed. We were
Exactly right.
just taking it. It is there with us. It's ours. It's like
Exactly right.
matter of right. It's like a matter of right.
Exactly. Exactly.
Yeah, we were assuming that oxygen, environment, air, everything is with us. We can use, abuse, misuse, whichever way we like. And
That's it.
then there is a push lesson. it's, a, it's it's a dose now. I don't know how long it is coming up, how long it will take, or maybe the lesson is lifelong for those who have observed this phenomena.
I say it is a great equalizer. Rich country like US has the highest number of deaths, highest number in the US compared on a per capita basis. Then you
Yeah,
see India, highly populated but not as bad in terms of
it's a
casualties in
equalizer.
India.
Yeah, but equalizer in we are trying to understand. Yeah, there is some equalizing occurring, but we don't understand. Is it by space, age, by health, by development, by area available to that country? US is 3 times in size probably, and they say 1/3 in population. I don't know
Right.
whether this data is correct or not, but then so how is this equalizing? You said just now.
Typically, you have like a famine, malaria. These things happen in Africa, Asian countries. Never happen in America or England or France or Germany. Never. But now they have. If you look at per capita basis, more cases of coronavirus than India per
Per
capita
capita.
basis.
Oh, you mean per capita energy utilization or other material?
Right.
Yeah,
Right.
yeah, yeah, yeah. Waste. They generate, yeah, developed countries waste 10 times, 50 times
Right.
more than
Exactly.
this country, where people reuse many things in India because of money, consciousness. People use a lot of materials in a daily way, they just reuse them, sometimes overly.
Exactly.
But yes, there is yes, per capita utilization of even power energy that you work in. I heard
Right.
some data. Even the packaging material on a daily basis in a developed country is too much. Yes, but how does it normalize or equalize? We have to see. Unless they learn the lessons, uh, how it will, how in this duration people will learn or not is the world to see now. We'll have to see that.
When I came to US many years ago, I would see the 2 liter glass Coke bottle. After drinking the Coke, they just trash it, the whole bottle. Glass bottle, nice. I said, why don't you clean it up, recycle it? This, the answer that I got then was, it is cheaper to get a new bottle than clean this up.
So
Because of
that's
the
the
labor cost. I was from Bangladesh. I couldn't accept that answer. Now they're recycling.
oh. Yeah. So see, they don't know what is the energy cycle versus material cycle.
Exactly right. Exactly
Material
right.
cycle versus energy cycle. One may be appearing cheaper than costly. Yeah. So these recycling might be appearing cheaper because it was most of the time they were looking for too much industrialization. That would bring
Exactly right.
industrialization to cheaper levels. But they didn't realize the environment issues probably.
Precisely. Precisely. That was the difference.
Yes, yes, yes.
So we'll see how it goes.
Yeah.
I've seen the world from both sides, from developing country, Bangladesh, India, like that, and the US, European side. Different frame of mind. Different frame of mind. In the West, we take things for granted. We had good hospitals, transportation, good roads, comfortable housing. But now Corona is teaching us that this is not the end of all. There are other things you should think about.
Yeah, see, no matter what you do, how much certain we may be because of development, the life remains uncertain. I mean,
Right. Right.
that is for sure. Probably, yes, in a developed country, we have a lot of things which are very, very certain. And to a younger generation, it sounds difficult to adjust to some uncertainties of any kind. And now it is the big uncertainty thrown before us.
Right.
Yes.
Right.
Yeah.
Right.
How is Anupama managing the time now? Are we exceeding the available time? Is it fine?
Okay, so yeah,
So if you permit, we can start.
so we are
Please
Yes.
follow your
Okay.
plan.
Okay. Thank you so much, sir. So greetings to global community. I am Anupama Thakur and I am the chair of IEEE ACSIR-CSIO student branch. And I welcome you all to IEEE Virtual Symposia 2020, which is themed on power and energy technologies. So as we all know that we are basically predominantly dependent on fossil fuels and coal reserves. And as with time they are depleting, we are getting deficit of energy. So there is a need for energy efficient technologies. There is a need for alternate energy sources, renewable energy sources, and many people should come up and take up these technologies. So focused on this, we are organizing this symposia, which is where we aim to broaden horizons and to renew the determination to serve not only the present energy demands but also fulfill future energy needs. So the goals of this symposia are: firstly, we are focusing on advancing global participation; secondly, educating future workforce; and thirdly, we are embracing standard leadership and networking. So with this brief, I would like to now first request our IEEE branch counselor, sir, for his welcome address. Yes, sir, Dr. Susanna.
Thank you, Anupama, Professor Saifur, Rahman, delegates of this virtual workshop conference meeting. It's really indeed a formal welcome from this IEEE student branch, students and the faculty of our campus, which is ACSIR-CSIO Chandigarh. And I also welcome the speaker of the day, Professor Rahman, who kindly agreed to share his expertise with us. I had a glimpse of his Google Scholar citations, and I really enjoyed looking at the keywords he has expertise for. And I'm really wondering that he would share his best of learnings during his whole career in US and other places. Particularly, I'm very much impressed by the title, the IoT addition to energy efficiency applications. The energy efficiency has been the issue for all engineers. IEEE is rather the prime institution of electrical and electronic engineers. They know much better than anybody else about energy efficiency. And when it applies to power sector, as he's the best known for, and how the efficiency has become so important in recent times. You know, pre-corona, we were always talking about climate. That means energy efficiency was always the issue. And now we are thinking, rather rethinking, the whole materials and energy issues in alternative or renewable energy manners. I hope he will share all those issues. I particularly have been impressed by the IoT, as I said, the intelligence being added to these systems at each, local level, at each distribution level, where intelligence on each system, subsystem, in a distributed manner could help maintaining their health, maintaining their best efficiencies, and even sometimes maintaining their interface with the nature when it comes to alternative or renewable energy sources. So I'm throwing these words as my quest for few queries, though people will have other questions during the session. So we are looking forward to a very interesting session from Professor Rahman in terms of this very relevant topic with best of his expertise and experience he already has, to the PhD scholars and other scholars, and I believe other faculty members who would like to listen to him. Welcome once again, and thank you for agreeing to be part of our community. And I would see that interesting deliberations come forward during this 1 hour or so kind of session. And I welcome everyone participating in this session, and I hope they will have interesting deliberations and questions at the end. So, not standing between the speaker and the audience now, I welcome and request Anupama to formally invite him for his sharing. Thank you once again and welcome.
Yes, sir. Thank you so much, sir. Now I take this privilege to formally introduce our speaker to the audience. So we have with us Professor Saifur Rahman, sir. He's the founding director of the Advanced Research Institute at Virginia Tech, USA, where he's the Joseph R. Loring Professor of Electrical and Computer Engineering. He also directs the Center for Energy and Global Environment. He is the Life Fellow of IEEE and an IEEE Millennium Medal winner. He was the president of IEEE Power and Energy Society for 2018 and 2019. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transactions on Sustainable Energy. He has published over 140 journal papers and has made over 400 conference and invited presentations. In 2006, he served on the IEEE Board of Directors as the Vice President for Publications. He is a distinguished lecturer for IEEE Power and Energy Society and has lectured on renewable energy, energy efficiency, smart grid, energy internet, blockchain, IoT sensor integration in over 30 countries. He is also the founder of BEM Controls, LLC, a Virginia, USA based building energy management solutions. He served as the chair of US National Science Foundation Advisory Committee for International Science and Engineering 2010 to 2013. He has also conducted several energy efficiency, blockchain, and sensor integration projects for Energy, Tokyo Electric Power Company, the US National Science Foundation, the US Department of Defense, the US Department of Energy, and the state of Virginia. And he has a PhD in electrical engineering from Virginia Tech. So with this brief introduction, I welcome you, sir, for your talk. Yes, over to you, sir.
Thank you, Anupama. Thank you, Dr. Sardana, for your nice introductions. Let me get started. And first page that you see here is what Anupama just said, so I will not depend on that anymore. So going forward, we have to understand that we, in this case, are looking at buildings, number one. Why that is important? Also, why is this energy efficiency IoT important for building context? In the US, over 90% of the buildings in the US are small size or medium size. Small size means 500 square meter. Medium means 5,000 square meter in their size. These buildings do not have any building automation systems because they are very expensive and these buildings can afford them. So we at Virginia Tech were given a grant by the US Department of Energy to build a platform, which we now call WISE Building Platform, that helps to do energy efficiency in commercial buildings as well as homes as we go forward. So this is the reason we got interested. I call this an open architecture platform for building energy efficiency. Why is it open architecture? Meaning you can deploy this solution in a building. Then if you want to add more applications, it can accept it. Typically, we do the red box on the lower right-hand side, heating, ventilation, air conditioning, lighting load, plug loads. Typically, that's what you do by building energy efficiency. Now I have added, you'll see later on, rooftop solar, storage battery, things of that kind. Also, you see in the yellow box on the upper right, bemcontrols.com. Make a note of that. If you want to learn more about how it is done, where applications have happened, where we are making other applications, please visit the website and see a lot of ideas you get from there. So now, this is a solution to sense and control all IoT-enabled equipment in commercial buildings. What is an IoT-enabled equipment? You have talked about air conditioning. It is a thermostat. So we use cloud-based smart thermostats to do the control, which we can remotely access. We do use smart plug, smart switches, and smart inverters, for example. So those are the applications. Those are the IoT devices in my case. This is my lab setup. The building is on the left-hand side. I have many kinds of thermostats, as you can see, different kinds, different manufacturers. I have variable aperture volume controller for air conditioning, smart lamps, smart switch, controller, smart ballast, smart plug, smart meters, and so on. All of these are either wireless devices, or I can use a analog versus IP driver. So the signal that I'm getting in the middle of the box, this could be a small Raspberry Pi unit that gets the signal from all these devices. The algorithm that is driving them is loaded on this Raspberry Pi, and it tells what to do. For example, if the room temperature is setting on a thermostat 20 degrees C, for example, when it goes to 21 degrees C, the AC comes on. So that knowledge that if temperature crosses 20 degrees C going up, turn the AC on. When the temperature drops and goes to 20 or below, turn it off. That kind of knowledge is built in this Raspberry Pi. We have now moved to the cloud-based. We do not use Raspberry Pi anymore because Raspberry Pi can fail, obviously. So we have moved to Amazon Cloud. Now all the algorithm is coming from Amazon Cloud via internet into all these devices, and they're being controlled. So I'll give you examples in a few minutes how that is done. This is the setup in my lab. That's what we are doing here. So as you see here, we're using standard protocols and COM technologies. Nothing is special here. Look at this page. The biggest strength that we have done, nobody has done to my knowledge yet, we are able to talk to any device using any of these technologies or data exchange protocols. Ethernet, serial interface, Zigbee, Wi-Fi, then you got BACnet, Modbus, web, then you have Zigbee API, Smart Energy Protocol, OpenADR. That is something some of you may know, that if you're a communication engineer, you look at IoT device run using IEEE 802.3 or 802.11, that's your Wi-Fi. Then RS-485, serial port. Then you got BACnet, OpenADR, Modbus. So what I'm saying, you can give me any device which uses any of these protocols, we can talk to it. That's our contribution. Now, how it is set up. If you focus your attention to the lower right-hand side of the screen, a building has what? It has heating, air conditioning, lighting load, plug load, some sensors, power meters, water meter, rooftop solar, storage, security camera. We can talk to all of the devices. Those are my IoT devices, talk to them. And then in the cloud for my system, I have an account for each of these buildings. So each building has a box in the cloud where this data about the status and the algorithm to control are loaded. And then you decide what to do with it. That's the architecture. Look at the upper right-hand side, the yellow writing in the green and blue box. We look at occupant comfort. We look at demand response, load control, energy savings, energy management, battery, building energy management, security, alarm notification, power consumption, peak load, all of that is going on in the algorithm. So this is how we have set up. So going forward, I believe our wise building platform can make any old building smart. This is very interesting. People think you have to build a building smart to begin with. But in the US, there are 6.3 million commercial buildings. All of the old buildings. We build maybe a few thousand buildings a year. But if you only focus on new buildings, what happened to the buildings that already exist? So our solution is they're all wireless devices. I don't need any wiring. I just take the new thermostat on the wall, replace the old one. I change the existing plug socket with a smart socket and so on and so forth. So that has allowed us to make some buildings I'll show you pictures of in a few minutes, smart. Okay, look at this. This is the result of our application. We typically save 20% or more energy by deploying the solution in commercial buildings. That's for heating and cooling applications. If you look at lighting applications, it's even more, 25%. But Dr. Sardana said, as you heard him, important to focus on energy efficiency because we cannot keep on building more and more power plants. So we have to look at how we can make the building efficient so that we don't use as much electricity to begin with. For example, in this case, 20% savings. If your building is old, you save 20%. That means what? You are leaving 20% energy unused. That electricity can be used by some other building. Also, what we have done in the application of voice building protocol, they are achieving improved maintenance operation, meaning you can see what the building is doing and you can maintain it remotely without having to send somebody over. And occupant satisfaction, that means we can monitor the indoor air quality in those buildings, and like CO2, VOC, PM 2.5, very important in Indian context, PM 2.5. And as those particles volume and density goes up, we can take some action to make sure that the threshold of acceptable PM 2.5 doesn't cross. That's an example of, to me, efficient building is not only saving energy, it is allowing you, the user, to work in a healthy environment. That's, for me, very important, healthy environment, the healthy air quality in the building. So going forward now, we have many applications. I'm giving you 4 examples here. These are real buildings, all old buildings. The first one is in Alexandria, which is close to Washington, D.C. Next, there is a classroom building for Virginia Tech, the top one. Then building for a local government, equipment bureau building. Then a lab building on our main campus in Blacksburg, Virginia. Then a building, a senior center in Maryland, not far from where Dr. Sadhana's son lived some years ago. So my point is we have deployed this solution in different kinds of buildings so that you don't have to have a shiny glass steel building to deploy this. Building could be any kind of building like this. So let's start with this building. This building, our campus or one campus building, 2,500 square meter, the energy consumption to 14 to 25 megawatt hour per month. Why the difference, 14 to 25? Because air conditioning load is high in the summertime, that's why 25. Winter time, no AC is less. Peak load 61. This building was built in 1947, before I was born. So my point is old building for sure, but we made it smart. How we did it, here you go. Classroom in that building. If you look at the upper left, we monitor the air conditioner on the roof, which is storing this classroom, and make a power consumption data available to my students who are managing it. We have put a thermostat in the smart thermostat in the room on the wall. We put a motion sensor to see students coming going. We put a smart load controller. Why smart load control important? This room has a printer and a computer and LED projector, LCD projector. What happens when the class is done, people leave, they do not turn off the computer. They don't turn off the printer. So we program this plug load controller, which is a plug socket. So after class over 9 p.m. or whatever it is, the things turn off automatically to save energy. On the top, I have a device called environmental sensor. It senses CO2, noise, temperature, and also humidity. And write it down here, also humidity. So you can now see how I made a classroom smart by putting sensors in that room to monitor what is happening and also control the thermostat setting, control the AC operation, control the printer and computer and all that. This is an example of how it is done. On the right-hand side, halfway up, BMOS core, that's a Raspberry Pi device, which is where algorithm is loaded and it takes these actions. It can be done locally or remotely as well, either one that you prefer. So look at this number, very important. I'm focusing now not on energy, monitoring the environment in the building, in the classroom that is. That classroom is used multiple times a day. One class meets from 6 to 9 p.m. and that's a 3-hour class once a week. You saw the building, the room is enclosed, no window in the room. That means when students come in, they breathe, obviously. As they breathe, you see the level of CO2 goes up. It's before they come in about 400 so per ppm, parts per million. Then as they come in, begin to go up, goes as high as 1100 parts per million. Then as they leave, it goes down to ambient, which is 400 or so. We discovered this by accident. We didn't. Our focus was energy efficiency, not monitoring CO2. But we had a sensor. We worked on that. What does this mean? If you ask doctors who talk about air quality inside buildings, if your CO2 level goes over 700 ppm, you begin to feel uncomfortable. It goes over 1000 ppm, you feel dizzy, lack of energy, and just uncomfortable. So this is what happens every time the class meets. So they didn't realize what was causing it until we discovered this. Typically, if you live or work in a building which is not very environmentally up to the standard, you will go home at night and feel kind of dizzy, uncomfortable, lack of energy. You tell your husband, wife, or father, mother, whatever the case is, I had a bad day at work. It's not a bad day. You're fine. The room was not clean enough. That was the problem. We discovered that. How we solve this now? As soon as the CO2 concentration that we're measuring in real time goes above 650 or so, below 700, we throw more fresh air into the room. You throw more fresh air, CO2 gets diluted, and then you're okay. That's how we solve this problem. That's what we talk about energy efficiency, but as well as indoor air quality. So I'm sure you have questions later on, but write your questions down. We can come back to this as we go forward. That's one case. Second case, in the same room, we want to show how much you can save both in terms of energy, kilowatt hour, and kilowatt peak by doing this control using wise building. So you see these graphs, will come back to this. Below the graph, I have a gray box and a yellow box. Gray box shows base case without wise building deployment. Set point 74, that's about 23 degrees C. Energy usage 2.7 kilowatt hour for some time period. Peak was 3.98 kilowatt. And on the right-hand side, I deploy wise building. Set point was raised to 25 in this case from 23. Energy usage dropped from 2.7 to 1.4. Peak load dropped from 3.98 to 0.5. What's happening? Let's look at the graph now. On the left half of the screen, the graph, you see these green lines and the blue lines. Blue lines represent the power demand when the AC comes on. And the green line represents the room temperature. If you just focus on one of the first case now, first day, first hour, I mean, you see AC came on, the tall blue bar. Then as a result, the green line fell. That means temperature went down to 23 degrees C. The AC stopped. Then AC stopped, room temperature slowly rises. You can see across red line is the setup, 23 degrees C. Goes up to about 24, 25. AC comes on because room is too warm. Then AC comes on, cool the room, and the AC comes back later on. That's how the normal process is. We have a situation here because of the pricing for electricity. Between 1 p.m. to 5 p.m., power is more expensive. If I can reduce my AC consumption for those 4 hours, I can save a lot of money. So this is, you see on the right-hand side of the screen, I raised the AC to 25 degrees C or 77 degrees Fahrenheit. Then AC is turned off. See, the blue line is off. Then time progresses up to 5 p.m. The temperature slowly rises from 23 to 25. When it rises 25, I turn the AC on. The net result is I was using in a different day 2.7 kilowatt hour for those 4 hours. I'm using 1.42. The peak load, the height of the blue bar, was about 4 kilowatt. Now it's 0.5 kilowatt because keep in mind, I turned the AC off, but I did not turn the ventilation off. This is unhealthy. When the fan was running, but not the compressor stopped. That's why I get the half kilowatt load. That's a fan load. So there's a summary is on the left-hand side, lower half of the screen. Before wise building deployment, 8.3 kilowatt hour, 8,340 kilowatt hour for the 3 months, June, July, August. 3 months data. Then for those same 3 months, the following year, after we deployed wise building 2016, I got only 6,000 kilowatt hour consumption. That gave me 26.8% savings. That's an example of how much can you save by deploying this kind of solution in a building that you are trying to monitor. Okay, moving on then. Next is another building with a bus depot on the ground level, an office on the upper level. This is the office on the upper level. Here, we focused on lighting control. Again, this floor, about 500 square meter space. We put lighting control or power meter to make sure we know what is the impact of our control equipment. We deployed the solution in 3 parts of the floor. One is the work area on the left-hand side, the big square. Then you have the cubicles where staff is working and a conference room. So what we did, we put lighting dimmer, as simple as that, nothing else, lighting dimmer when the demand is less. Or look at this case where you have the bigger box on the left-hand side. This space has skylight. So typically skylight brings in a lot of light during daytime, but light that you see here are never dim. They're left alone all the time. This is a standard cultural thing here. We said, why do you have to keep the light on at 100% capacity when you get sunlight? But they say, we don't want to turn the lights off. If you turn them off, people don't feel comfortable. We leave them on. Now we deployed our solution. As a result, we monitor the incoming sunlight into the space. And as the sunlight increases, we slowly dim those artificial lights. So the total illumination is the same, but it is sum of sunlight and the artificial light. That's the difference. On the right-hand side, the top picture for the work area for the staff. When they go to lunch, we dim the lights. By dimming, we save energy. Conference room, typically what happens? When the staff comes in the morning, they turn the lights on in the conference room. It stays on all day, stays on, regardless of whether people are using the room or not. So what we do, we don't turn them off. We dim them more during unoccupied times and less when they're occupied. For example, you might say, well, maybe in your office, in your conference room, you got a occupancy sensor. Nobody's around, light goes off. This is a problem. Light goes off is not what we want. We want light to dim. That's the difference. My office has also occupancy sensor. So in my office, as I come in, light goes on. But then I'm sitting at my desk, not moving my hand or moving around too much, light goes off. That's not something I want. So we don't turn the lights off, we dim them to some level. As a result, you see, we did a data for almost 10 months, October 16 to June 17. We saved about a third, 34.5% electricity was saved just by dimming and scheduling. So let's move on then. This is the summary, how I got the 34% number. I give you data for 3 months, October, November, December 2016. Look at the middle column. Middle column is total energy consumption without any dimming, not off, dimming. On the left-hand side is energy consumption after I deployed the dimming algorithms in that building on that floor. So over 3 months before dimming, I was using 1250 kilowatt hour. With dimming, I am using 823. So that's 34.1% savings. And at the bottom, just for recording purposes, I put the number. The dimming level is down from 6:30 to 9 p.m. After that, you turn it off, of course. Then some office area, 50% dimming, some 45%, some 60%. Where these numbers come from? We have machine learning algorithm, which looks at the behavior pattern of the people using that space. And based on that, we determine when they go to lunch, when they come back, when the more work is done, when somebody is using the Xerox machine, all that kind of stuff. And based on that, we came up with these numbers. But these numbers are not fixed. If you think the conference room B is 45%, you say that's not enough light. You can just change it to any number you want to, from a smartphone or any laptop. You can do that easily. So that's the way we managed it. The next slide is our building where I work, rooftop solar. I'm showing you here. We're using the Wise Building platform, IoT platform, to control the output of the rooftop solar. Why is it important? You know, you are using solar in your rooftop in your home, for example, and you are not home 10 o'clock in the morning, no AC running, no cooking going on. You're producing more solar than you need. So the net output goes to the distribution line. That's standard practice. Problem is, on your street, in our case in Virginia here, there are many homes which have rooftop solar. So all of them begin to send power to the distribution line, which is being fed already from the substation. The voltage goes up. In the US, the regulation is the voltage has to be maintained plus minus 5% of rated. Rated is 120 in the house. It can be as high as 126 or as low as 114, not outside that limit. If you're putting so much solar from these homes on the street, it goes to 10% overload. What do you do? The power company has a policy that if that happens, they'll turn off your inverter. You cannot sell any power back to the grid. You don't want that. You have invested money expecting to sell some energy when you're not home. That is now turned off because voltage profile has exceeded the upper. What we have done, you see the next picture. We are putting our Wise Building platform connected to this smart inverter, which will tell me all the data you see, the AC power, DC power, voltage, current, power factor, wind speed, solar radiation, all this data is coming from Wise Building platform. And then if you follow the lower yellow box, yellow line box, smart inverter control, you can see the bar here, the white bar. It shows you at what power factor you're running it, and what output you're running it. That can be automatically controlled. For example, if you are sending power to the distribution line and your voltage measured at 108% of the nominal voltage, which is 100%, you will automatically slow down the AC power coming out of the inverter. Then power company cannot complain because you are maintaining the voltage in that profile. And nobody has done this work. This is something we have done because we are seeing now in the US, many like California, Florida, and Hawaii, this problem has happened because of the high voltage. So we have solved that problem using wise building. This is not energy efficiency, by the way. I said on the way back, we have built an IoT platform that can take any device that you want to control. So here, the solar inverter is an IoT device to control this, as an example. Okay, now battery storage, we put the platform in a building that we use as classroom. It's a very small battery, 5 kilowatt, 12 kilowatt hour battery. And this is how it shows up on my screen for the device building platform. I can see the battery status. I can see the charging status. I can see it is charging, discharging. All of that information is given on one platform. So now you saw the building energy, heating, cooling, smart plug, smart switch, rooftop solar battery. All of that is done from one application. So we believe that all buildings should be smart buildings. It doesn't cost as much, just the effort you put in and monitor this. Again, if you want to know more, go to this wisebmcontrols.com website. It has a demo, a lot of data, and explaining how it works. So with that, let me come back to the end of my slideshow. Just remind some of you who are IEEE voting members, I'm running for IEEE president this year. Election will be held between mid-August to end of September. I have been, as Anupama said in the beginning, PS president. I was a past chair of IEEE Publication Board. I have set up PS University. So if you're a PS member, you go online for free and get a lot of webinars, a lot of training materials. I have done the corporate engagement program. In fact, Bangalore Electric Supply Company, Westcom, is a member of this program in India. And also I have formed councils in India, China, Africa, Latin America, all of that. These are my websites, srahman.org, Facebook, LinkedIn, whatever you are comfortable with, visit them, and I will be happy to answer questions. I'm done.
Yeah, thank you so much, sir, for a very insightful session. So now the session is open for question and answers. So I request the participants, if you want to directly interact with sir, so the session is open. Yes, any questions?
If you send a text message, you can read it to me from the chat box.
Yes, sir. Yes, sir. I'll read it. But for now, they have just appreciated the session. So no questions yet. So anyone?
Anupama, can you hear? Hello.
Yes, yes, sir.
Yes, I can hear you.
Yes.
Yes, you are audible.
He's breaking up.
Yeah, Parihar sir, your voice is breaking.
Voice breaking up.
Yes, Parihar sir, your voice is breaking. So you can try again little later. Yes, sir. In the meanwhile, there is one question. Yeah. So the question is, what is the cost of this entire real-time monitoring system, sir?
Right, very good question. Depends on what you want to do. Example I gave you for our classroom building, we deployed 6 thermostats, 1 power meter. It cost us about $1,000 US. And there's a monitoring cost also, which is about annual basis, maybe $200 per year. That's the cost. $1,000 investment, including labor costs, another $200 per year to monitor, control, and give you access to the data.
So much, sir. So now, Parihar sir, if you want to again reconnect, you can ask, then we can take up your question. I hope I'm audible. Is
Maybe
any
he
other
can,
question?
maybe he can write in the chat box.
Sir, I have one question. Sir, for the calculation of efficiency of the power saved, so you have used only algorithmic studies, or you have used some past analysis?
Use some past data.
Yeah, past data, past consumption of during that period. Have you
Of
tried?
course, you're right. You remember this building I showed you, the 4-story building with a classroom? Before we deployed our solution, we went and measured what's happening without us coming in the building to begin with. That's my reference case. Then we deployed the solution and compared the case with the solution and before the solution was implemented.
Sir, something might have changed.
Well, this is a very good point. When we compare similar days, otherwise not fair. So we also monitor the outdoor temperature, occupancy, and the building usage. So when we deploy the solution, we monitor the temperature outside. We only compare the historical day with known power consumption and known outdoor temperature. Then we pick a day after deployment which has similar conditions, meaning same outdoor temperature, same occupancy. Therefore, the comparison is 1-to-1.
Sir, but in in the case scenario, when if we conditions, what will
One point is we will save energy, but we cannot say I saved 30%. I cannot say that because 30% of what, right? So maybe the weather was cooler that day, so I use less because of the cooler weather, not because of the wise building deployment. You get the point?
Yes, sir, I got the point.
Overall, if you do for a whole year, then you expect that the diversity of the temperature will average out.
Okay. Thank you, sir.
Any other question? Yeah. Any other question?
Uh, uh, there is one question from there is a question from the YouTube asked by Mr. Sanjay. Why the panels are not oriented towards the sun's direction?
Good question. The most efficient panel inclination is, if you don't want to track it, of course, tracking is different, is same as the latitude of the location. So my latitude here 38 degrees, but my panel is not tilted 38, much less than that. We have done some calculations. It is more expensive to tilt it 38 because of wind loading. The roof is open. It's a 10-story building. So then the building architect would not allow us to tilt it at 38 because that loading goes up on the roof of the building. So we are limited to how much we can do. But by tilting not 38, maybe right now it's about 20 degrees or so, we lose something, you're right. But we gain more in the summertime. Summertime sun is high in the sky. So that if you make it flat, it is more energy than making it tilted. Tilted is good for the winter time when the sun is low in the sky. Here, a very good observation, but that's the reality that we have to face.
Hello.
Thank you, sir.
Hello.
Yes.
Yes,
Hello, sir.
Malhar sir, you're audible.
Yes, I'm audible.
Yes, you are
Yes.
audible.
Okay. Sir, I would like to know what protocol has been used to control the data coming from different sensors to the control unit.
Okay. It depends on the sensor itself, like thermostats, they use Wi-Fi protocol. The power meters, they use BACnet protocol. For the rooftop solar, uses Ethernet. So we are flexible, but depending on the sensor itself, sensor decides what protocol it was built with, obviously, by the manufacturer. But we know the protocol and we can translate that any protocol. I showed a list of about 6 or 8 into the Python-based algorithm that we are deploying to run the sensor.
Okay. Thank you, sir.
Sure.
Yeah. So, sir, there's one question from a YouTube viewer, and her name is Manjari. So she's asking that that you have mentioned about light dimming in your presentation. So she's asking, is it a manual dimmer or is it automatic? Does scotopic or phototopic ratio plays role?
Right. Very good question. We put a light sensor in the room. For example, you saw the open area with the skylight. There's a sensor on the wall which senses the lumen level of light intensity in the room. As the sunlight becomes stronger, the lumen level goes up. Typically 550 or so is a standard number. It goes to 700. When the lumen level exceeds the threshold, the signal goes automatically to the light controller to dim the light. It's all manual. And as the sunlight begins to reduce, then the light will slowly come back up to maintain the required total light intensity in the workspace. The answer is yes, it is automatic, and that's how the control takes place.
Okay, thank you so much, sir. Any other question from the participants? Because I cannot see any more questions in the chat box window. Before we end up today's session.
I had few questions. Can I ask one or two?
Yes, yes, sir. Yes, sir.
Yes, sir.
Professor Rahman, I'm very keenly listening to you. I was wondering when you mentioned about light, temperature, and the whole environment sensing. Wonderful to see that concerns. I'm wondering the two issues that I still have. One is related to the lady who asked about light. I'm asking, is it that we can generalize the needs in that room? No, what about the human elements? Sometimes, these automatic systems push people to think, what is this happening automatically? What is that? Where is my concern? Or if there are many people in that room. So those issues remain somewhere, how to manage them. The human issues. Human preferences, anyway, human preferences.
That is true. We have faced that same question. So that is why we made this user intervention. That means if the staff says the filing cabinet area is not enough light, for example, it's possible. So we gave the secretary in that office an algorithm on her laptop. She just move her finger on this bar to change the intensity in real time. It can be done. Similarly, normally what happens? You have a thermostat, you're feeling too cold, AC is too strong. You cannot do anything typically, you just live with it. In this case, the staff tells secretary, my room is too cold. But she will just go to the thermostat controller and move it to a higher temperature and see if she's okay with it. And if she's okay, leave it there.
Oh, that's very nice. One more question, if there is none, by the way, about the sensitivity of such a system, or in terms of some absolute or objective ways of performance of such a system, because it becomes unique system. You mentioned about daily energy saving or annual and the weather changing. Particularly if I say sensitivity as to how much of wastage it is still able to, allow, or like how much of disturbance it is able to sensitize towards adding intelligence to the system. So is there any measure like that sensitivity of, although probably it would depend on sensors, I believe, but still I'm wondering how this is managed in the system.
Well, if you talk about temperature sensitivity, for example, we've done studies that women like warmer temperature, men like cooler temperature. That's an example. So how do you deal with that? Then we have a building at Virginia Tech here where the building is heavily instrumented by vibration motion. And they can tell from the motion, the men walk differently than women walk. They can tell, are there mainly women there or mainly men there? And based on that, they can sensitize the temperature setting.
Wonderful.
Like in the US, very, very true. US, like Washington, D.C., if you've been here yourself, you see in the summertime, people wear a jacket and tie. Summertime. That's culture in this city. As a result, they must keep the temperature in the office room maybe 19 or 18. So you can wear a tie and a suit and feel comfortable. But that's to me a wastage. So why not keep it 22 and drop your jacket and hang it on your door, whatever it is. So my point is this system I described here today allows you to do that. It is called micro level control at the workspace, not for the whole floor at one time.
Wow. That's very good.
My policy is, doctor, my policy is I will control the temperature, the lighting, the ventilation. You will not know I'm controlling it. If you do not know, you cannot complain. You will not complain. That's my philosophy.
Yeah. So it will be invisible.
Right.
Invisible kind of control.
Right. Then it's ubiquitous. You don't know it's happening. Then you cannot complain.
Yeah, that's very good. Very good philosophy.
That's my philosophy. That way I am nobody's enemy.
Because if they can put a finger on somebody, they will like to.
Right. Right.
If they cannot blame weather, they will blame the person who controls the weather.
Correct. Exactly.
Yeah. How are we doing, Anupama?
Yes. So we have one last question. So the girl who asked about the light measuring, the light dimming. So she's saying that is there a light dependent resistor placed in the system for measuring the light intensity?
Okay, there are two answers to that question. One is the intensity and one is control, how I do this. Intensity wise, there is a sensor which changes voltage based on amount of light. So that voltage change gets translated to the sensor and comes to me. That voltage from 0 to 10. If it is 10, that means 100%. If it is 5, means 50%. That's how I get that information. That's the sensing part. Controlling part, at the circuit level, at the beginning of the circuit, is feeding all those ceiling lights. At the beginning of the circuit, I put a controller, again 0 to 10 volt controller, which will send a signal, dim the light to 80%. So drop the voltage to 8 from 10. That gets transformed into changing the voltage available to the lighting circuit and light dims. You're right, it is control based on voltage level fed to the light fixture.
So that's all, sir. Thank you so much for the very insightful and fruitful session. So I request Sardana sir to formally thank sir before we end up today's session.
Okay, good set of questions. Thank you very much.
Yeah, Professor Saifur, Rahman, indeed, wonderful sharing. Interesting questions have come in, and it is probably sensitizing the engineers towards, sometime I read the whole engineering is energy and environment. So now from energy efficiency, power efficiency, we have seen the environment playing role because there are humans into it. And once this happens, people will see the systems, not just efficiency, but more effectiveness. So it's really a management term wise also, it's probably moving from efficiency to environment effectiveness, wherein humans element gets into. I believe these lessons would go a long way to all the research scholars who have heard it from your experience, how to do them and how to achieve the best performances. And also we wish you good luck uh, for this elect 2020. How far are we from that?
Well, the election starts on 17th of August for 6 weeks. It'll be all online. All IEEE voting members get an email from IEEE. This is the election time, the 3 candidates, XYZ, and you just click on the name and you vote for this person, and that's it.
Wow. So our vote is more or less fixed now.
I hope so.
It's no more. It's an open secret. So we wish you good luck and we wish to see you at that chair position. And we thank you formally from on behalf of the whole chapter, the people who attended and those who will follow you on YouTube. And I hope a lot of lessons from this from your lecture. And I hope, who knows, a lot of collaborations likely to follow. Thank you very much, and best of luck and best of health at your place.
Same to you. Thank you very much.
Yes. So now I request everyone to turn on their video. We can have a group photograph with sir. Yeah, so before we end up today's session. I request all the
Shall
participants.
I end the show, Anupama? End the show?
Yes, sir, you can end the show. Yes. I request everyone who are joining us to kindly turn on their video.
Thank you, sir. It was a wonderful session.
Yes, sir. Any more people joining us? The photograph?
I can only see Anupama, you, or nobody else I can see on the screen. I can see you.
I can, sir,
Yes.
Yes, sir, I can see the grid. Yeah, so I'm capturing the photograph. So everyone please smile. Okay, so thank you. I've taken the shots. Yes, thank you so much, sir, for joining us. It was a privilege to have you with us.
Thank you.